Hello, friend. Welcome back to another quiet journey through the cosmos. Some nights the sky feels closer than it should. Stars pulse in patterns we almost recognize. Silence wraps itself around questions we've carried since childhood. And sometimes, if you listen carefully enough, the universe whispers back. Tonight we're going to drift through something extraordinary. For decades, humans have pointed telescopes and radio dishes toward the heavens, hoping to catch a message, a pattern, a sign that we're not alone in this vast darkness. And we've heard things, strange things, signals that make no sense, bursts of energy that defy explanation, whispers from the void that appeared once and never returned. These aren't stories. They're real events recorded by scientists, preserved on paper and magnetic tape studied for years without answers. The universe sent us letters, and we still don't know what they mean. Before we begin this gentle exploration, if you find comfort in these quiet nights of wonder, you might like to stay a while. You can gently tap the like button, subscribe, if you'd like more stories told softly, and ring the little bell, not for noise, but so the next quiet night can find you again. It helps this small corner of the internet continue to exist, and I'm grateful you're here. Now, let's drift. Tonight we'll move slowly through the most mysterious cosmic signals ever recorded. Not with urgency or alarm, but with the patience of someone sitting beside a telescope at 3 a.m, waiting for something that might never come. We'll explore the wow signal, those impossible fast radio bursts, the perfect timing of pulsars and stranger things still. We'll talk about what we know, what we don't, and why the mystery itself might be the most beautiful part. You don't need to understand everything. Just rest and let curiosity do the listening. The universe has been speaking. We've just been learning how to hear. In 1977, on a warm August night in Ohio, a man named Jerry Amon was doing what he did most nights, reviewing computer printouts from the Big Ear radio telescope. This wasn't glamorous work. Mostly it was noise, random static from distant stars and galaxies. The background hum of a universe that seemed indifferent to our listening. Sheet after sheet of numbers, almost all of them unremarkable. Almost all of them. Exactly what you'd expect from empty space. Then he saw something that made him grab a red pen. The signal lasted 72 seconds. In that time, it rose from nothing to a strength 30 times greater than the cosmic background noise, held steady, then faded back into silence. The frequency was 1420 megahertz, right in the protected spectrum known as the water hole. A bandwidth so special that international law forbids human transmissions there. It's called the water hole because it sits between the frequencies of hydrogen and hydroxyl, the components of water, and scientists have long theorized that any civilization trying to communicate across the stars might choose this quiet, protected channel. Amon circled the signal's intensity on the printout and wrote one word in the margin. Wow. That exclamation, scribbled in red ink on a long strip of computer paper, became the name of the most famous unexplained signal in the history of astronomy. The wow signal. A cosmic postcard that arrived once and never again. Scientists suggest the signal came from the direction of Sagittarius, somewhere near a cluster of stars called Chi Sagittarii. But when they pointed their telescopes back at that exact spot again and again over the following weeks, months, and years, there was nothing. Just the usual whisper of background radiation. Whatever sent that signal either stopped transmitting, moved, or was never there in the first place. Some researchers believe it could have been a natural phenomenon, perhaps a rare event involving a star or nebula we don't yet understand. Others point to the frequency, the duration, the intensity, and wonder if it was something else. A broadcast, a beacon, a signal from someone somewhere saying hello into the dark. What's remarkable isn't just the signal itself, but what it reveals about the nature of cosmic listening. We imagine that if intelligent life exists out there, they'd be broadcasting constantly, like radio stations that never go off the air. But what if that's not how it works? What if signals are rare brief, and we've only just started learning how to catch them? Think about it this way. Humans have only been seriously listening to the cosmos for about 60 years. That's less than a human lifetime. In the scale of cosmic time, we've been listening for the equivalent of a single heartbeat. And in that heartbeat, we caught something. A 72-second anomaly that we still can't explain. Some people hear about the wow signal and feel disappointed that it never repeated. They call it a mystery without a solution, a question without an answer. But perhaps that's the wrong way to look at it. Perhaps the signal did exactly what it was supposed to do. It reminded us that the universe is stranger than we think. It taught us that if we keep listening, we might hear something that changes everything. Scientists have proposed dozens of explanations over the decades. Maybe it was a comet passing through our line of sight at just the right moment. Research in 2017 suggested that comets can emit hydrogen at the right frequency, and 2 comets were in that region of sky in 1977. But other scientists pointed out that the signal was far too strong and too narrowband to match what comets typically produce. The debate continues quiet and unresolved, or maybe it was a satellite, a piece of human technology reflecting signals in a strange way. But the Big Ear telescope was designed to filter out terrestrial interference, and the signal's characteristics didn't match anything from Earth. It rose and fell exactly as you'd expect, from a source fixed in the sky as Earth rotated beneath it. Whatever it was, it seemed to be out there, not up here. There's a common misconception about the wow signal that's worth addressing. Many people assume it was a repeating message like a radio station that you can tune into anytime. But it wasn't. It appeared once for 72 seconds and then vanished forever. This makes it almost impossible to study. In science, repeatability is everything. If you can't observe something twice, you can't measure it, properly can't rule out error, can't build a theory that holds together. And yet, the wow signal's greatest strength might be its singularity. It can't be dismissed as a glitch because the equipment was checked and rechecked. It can't be ignored because the data is clear preserved on that original printout, still stored at Ohio State University. It happened. Something out there for just over a minute spoke louder than the background noise of the universe. Here's a question worth sitting with for a moment. If you could send a message to the stars knowing it would take centuries or millennia to reach anyone, what would you say? Would you send a constant broadcast repeating forever, hoping someone eventually tunes in? Or would you send a single powerful pulse, a brief shout into the void, and then go silent? Maybe the wow signal was exactly that. A civilization's way of saying, we were here, we existed. We looked up at the same stars you're looking at now. And maybe that's enough. The lesson of the wow signal isn't about aliens or technology or proof of anything. It's about humility. It reminds us that the universe doesn't owe us answers. It doesn't repeat itself on command. It doesn't make things easy. But if we're patient, if we keep building our telescopes and refining our methods and listening through the static, we might catch something extraordinary. Not because we deserve it, but because the cosmos is vast and strange and full of things we haven't imagined yet. Jerry Eman, the man who discovered the signal, spent the rest of his career cautious about its meaning. He never claimed it was aliens. He never wrote best-selling books or gave grand lectures about extraterrestrial contact. He simply said that it was the most interesting signal he'd ever seen and that he wished it would happen again. That's the mark of a true scientist. Not certainty, but wonder. But not conclusions, but careful, patient curiosity. 47 years have passed since that August night. The Big Ear telescope was demolished in 1998, torn down to make room for a golf course. But the data remains that red wow still visible on the original printout, a monument to the moment when something somewhere might have been trying to reach us. We may never know what caused the wow signal, and in a way that's perfect, because the greatest discoveries aren't always about finding answers. Sometimes they're about learning how to live with beautiful, unanswerable questions. They're about accepting that the universe is bigger than our understanding, older than our civilizations, and far more mysterious than we can measure. So, Tonight, as you close your eyes, think about that 72-second window in 1977. Think about Jerry Eamon sitting in a small room in Ohio, seeing something no one had seen before. Think about the signal rising from silence, holding steady, then fading back into the cosmic background. And remember that somewhere out there in the vast dark between stars, something might still be whispering. We've just begun our journey through the cosmos tonight, and already we've touched something profound, something that refuses easy answers. The wow signal taught us that the universe doesn't shout, it murmurs. And if we want to hear it, we have to learn patience, precision, and the art of listening in silence. But that single mysterious signal from 1977 is just the beginning. Because while Jerry Eamon's discovery whispered from the past, there are other signals, thousands of them screaming from distances so vast they make our galaxy seem small. Signals that arrive in bursts shorter than a heartbeat, carrying more energy than our sun produces in decades. And unlike the wow signal's gentle mystery, these cosmic screams demand we rethink everything we thought we knew about the universe. In 2007, a graduate student named David Narkovich was sitting in a library at West Virginia University reviewing old telescope data that had been collecting dust for 6 years. He wasn't looking for anything in particular, just doing what graduate students do, combing through archives, hoping to find something interesting enough for a thesis. The data came from the Parkes Observatory in Australia, recorded back in 2001, routine observations of the Magellanic Clouds that had already been analyzed once and filed away. Then he saw it, a spike, a burst of radio energy so bright, so brief, so impossibly powerful that at first he thought it had to be a mistake. The signal lasted less than 5 milliseconds, 5/1000ths of a second. In that microscopic instant, it released as much energy as the sun produces in an entire day. And it came from somewhere beyond our galaxy, somewhere billions of light years away in the deep cosmic dark. David brought the data to his supervisor, Duncan Lorimer, an astrophysicist who had spent decades studying pulsars and radio astronomy. Together, they checked the equipment ruled out. Interference ran the numbers again and again. The signal was real. It had happened, and it had come from a distance so vast that the universe itself was significantly younger when that energy was released. They published their findings in 2007, and the astronomical community gave the phenomenon a name: fast radio bursts, FRBS, cosmic screams in milliseconds. What makes fast radio bursts so profoundly strange isn't just their power or their brevity. It's that for years after the first discovery, scientists couldn't find more of them. That original burst, now called the Lorimer burst, seemed to be a fluke, a one-time event that might never repeat. Astronomers searched the skies, reviewed old data, built new detection systems, and found nothing. Until they did. In the years that followed, more bursts appeared. FRB 110220. FRB 121102, FRB 180814. Each one a flash of impossible energy from the distant universe, each one raising more questions than answers. Some came from spiral galaxies like our own, others from small, dim dwarf galaxies billions of light years away. Some appeared once and vanished, others remarkably repeated. Scientists suggest that fast radio bursts might be caused by magnetars, a type of neutron star with magnetic fields so intense they warp the very atoms around them. Research shows these objects can release enormous bursts of energy when their crusts crack or their magnetic fields reconnect. But that's just one theory. Others propose colliding neutron stars, evaporating black holes, or phenomena we haven't even imagined yet. Here's what we know for certain. Fast radio bursts are real. They happen all the time. Conservative estimates suggest thousands of them occur across the observable universe every single day. Most of them we never detect because they're not pointed in our direction, or they're too faint, or they happen in wavelengths we're not monitoring. But they're out there flashing in the dark, like cosmic lightning, each one a mystery wrapped in mathematics. The energy involved is almost impossible to comprehend. Imagine taking all the power the sun has generated over 80 years, every photon of light, every flicker of heat, every particle of radiation, and compressing it into a burst shorter than the blink of an eye. That's what we're talking about. That's the scale of these events. And they're happening billions of light years away, which means the actual energy at the source is even greater than what we detect after it's traveled across the universe and faded with distance. One of the most fascinating discoveries came in 2016, when scientists realized that FRB 121102 was repeating. Not randomly, but in patterns. It would go silent for weeks or months, then burst again. This was revolutionary because it meant they could predict when to watch, where to point their telescopes, how to gather data that single-burst FRBs could never provide. The repeating bursts came from a dwarf galaxy 3 billion light-years away, a small, unremarkable collection of stars in a region of space we'd never paid much attention to. But now, suddenly, it was one of the most observed objects in the cosmos. Teams from around the world coordinated their telescopes, capturing bursts in multiple wavelengths, tracking patterns, building models. And what they found was even stranger than expected. The bursts weren't just bright, they were twisted. The radio waves showed signs of scattering, as if they had passed through some incredibly dense medium on their way to us. Scientists believe this might be evidence of an extreme environment, perhaps near a supermassive black hole or inside a supernova remnant. Whatever is producing these bursts isn't floating peacefully in empty space. It's surrounded by chaos. There's a common misconception about fast radio bursts that's worth clearing up. When people first hear about them, especially in popular media, there's often speculation about alien technology. Could these be signals from advanced civilizations, messages, or perhaps even byproducts of massive alien engineering projects? It's not impossible, but it's deeply unlikely. The problem is that FRBs come from such enormous distances and release such tremendous energy that any civilization capable of producing them would need technology far beyond anything we can imagine. We're talking about harnessing the power of entire stars, projecting it across billions of light years, and doing it in millisecond bursts. It's theoretically possible, but nature has simpler, more plausible explanations. That said, the mystery remains open. Some FRBs show patterns that feel almost structured. FRB 180916, discovered in 2018, repeats on a 16-day cycle. For 4 days, it's active, bursting multiple times. Then it goes silent for 12 days. Then it starts again. We don't know why. Scientists suggest it might be related to the orbit of the object, producing the bursts, or perhaps some kind of precession in its magnetic field. But the precision of the cycle is remarkable. In 2020, something extraordinary happened. Astronomers detected an FRB coming from inside our own galaxy, FRB 200428. It came from a known magnetar called SGR 1935 plus 2154, located about 30,000 light-years away in the constellation Vulpecula. This was the first time scientists could definitively link a fast radio burst to a specific source, and it seemed to confirm the magnetar theory. When the burst occurred, X-ray observatories also detected a simultaneous spike in high-energy radiation. The object was doing exactly what theoretical models predicted. But here's the strange part. The burst from SGR 1935 plus 2154 was far weaker than the extragalactic FRBs we'd been detecting. If it had occurred in another galaxy billions of light-years away, we might not have noticed it at all. This raises an uncomfortable question. Are the distant FRBs fundamentally different from the one in our galaxy? Or are we only detecting the most extreme, most powerful bursts while thousands of weaker ones go unnoticed? Think about it like this. Imagine you're standing in a dark field, and far away across miles of night, someone is flicking a lighter. You'd never see it, but if they ignited a flare or set off fireworks, the light would reach you. Fast radio bursts might be the same. We're only catching the cosmic fireworks, the absolute brightest events, while countless smaller signals remain invisible. The Canadian Hydrogen Intensity Mapping Experiment, known as SHIME, has revolutionized FRB detection. It's a telescope designed not to look at one small patch of sky, but to monitor a huge swath of the heavens continuously. Since it became operational, SHIME has detected hundreds of fast radio bursts, more than all previous observatories combined. And the data keeps coming faster than scientists can fully analyze it. What's emerging from this flood of information is a picture of incredible diversity. Some FRBs are bright and narrow band concentrated in a specific frequency. Others are broad and diffuse, spread across the radio spectrum. Some arrive in clusters, multiple bursts within seconds of each other. Others are solitary. Some show signs of polarization, suggesting strong magnetic fields. Others don't. It's as if we've discovered a new category of cosmic event, but instead of one type of phenomenon, we've found an entire zoo of related but distinct processes. Like discovering lightning and realizing there are dozens of different kinds, each with unique characteristics. Here's a question worth considering as you drift towards sleep tonight. What does it mean that the universe is full of these brief, violent explosions of energy, and we only just learn they exist? How many other phenomena are happening constantly and visibly, waiting for us to build the right instruments and ask the right questions? The lesson of fast radio bursts isn't about aliens or catastrophes or the end of anything. It's about humility and patience. For billions of years, these bursts have been flashing across the cosmos, and we never knew. They didn't wait for us to be ready. They didn't announce themselves. They simply existed indifferent to our ignorance. And now, we're learning. Slowly, carefully. Building better telescopes, developing new theories, watching the sky, with instruments that can catch events lasting less time than it takes to snap your fingers. We're learning that the universe is louder than we thought, stranger than we imagined, and far more active than the serene darkness suggests. Some scientists believe that fast radio bursts might one day be used as cosmic rulers' tools for measuring the distribution of matter across the universe. As radio waves travel through space, they interact with free electrons, getting slightly delayed. By studying this delay, researchers can map the invisible material between galaxies, the warm ionized gas that makes up the cosmic web. FRBs, because they're so bright and come from such vast distances, are perfect for this kind of measurement. Others see them as laboratories for extreme physics. The environments that produce these bursts involve magnetic fields, densities, and energies that we can't replicate on Earth. By studying FRBs, we're studying conditions that exist nowhere else, learning about how matter behaves when pushed to its absolute limits. But perhaps the most important thing about fast radio bursts is simply this. They remind us that the universe is still surprising us. Even now, in an age of advanced astronomy and space telescopes and supercomputers, the cosmos can show us something we never predicted, something that doesn't fit neatly into our models, something that demands we think harder and look deeper. The Lorimer burst happened in 2001, but we didn't discover it until 2007. That means for 6 years, the data sat in an archive unnoticed, waiting. How many more discoveries are hiding in old data, overlooked or dismissed? How many future breakthroughs are already recorded, just waiting for someone to look at them the right way? As you close your eyes tonight, think about those millisecond bursts traveling across billions of light years. Think about the energy they carry, the mysteries they hold. Think about David Narkovich in that library finding something no one had seen before, something that would change our understanding of the universe. And remember that these cosmic screams, these impossible flashes of power, are happening right now. Somewhere in the distant universe, a magnetar is cracking, a neutron star is collapsing. Something we don't yet understand is releasing energy that will travel for eons before reaching our telescopes. The universe is not silent, it shouts. We're just learning how to listen. But while fast radio bursts arrive in chaotic, unpredictable flashes, there are other signals in the cosmos that do the opposite signals, so precise, so relentlessly regular, that when they were first discovered, scientists genuinely wondered if they had found evidence of alien technology. These aren't screams, they're ticks. Perfect, unceasing clockwork pulses from objects that shouldn't exist at all. It was late July 1967, and Jocelyn Bell Burnell was 24 years old, a graduate student at Cambridge University, working on a project that most people would have found mind-numbingly tedious. She was analyzing chart recordings from a new radio telescope looking for quasars, distant galaxies with bright cores. The data came in as ink traces on paper, miles and miles of it, scrolling out day after day. Her job was to study every inch looking for anything unusual. Most days there was nothing, just the random crackle of cosmic noise, the background static of a universe doing what universes do. But on one particular afternoon, she noticed something odd, a little bit of what she called scruff. A tiny irregularity in the trace barely noticeable, lasting only a fraction of a second. It didn't look like a quasar. It didn't look like anything she'd seen before. She marked it and kept watching. Days passed, then weeks. And then impossibly the scruff appeared again. Same location in the sky, same time of day adjusted for Earth's rotation, same pattern, a signal, regular, repeating, pulsing. Jocelyn brought the finding to her supervisor, Anthony Hewish. Together they confirmed what seemed impossible. The signal was arriving in pulses, each one lasting about 1/30th of a second, separated by exactly 1.3 seconds of silence. Tick, silence, tick, silence, tick. Over and over, with a precision that seemed almost artificial. The team joked about it being LGM1, Little Green Men, because what natural object could pulse with such perfect regularity? What in the universe could keep time that precisely? They knew it was probably something natural, something they didn't understand yet. But for a few weeks, the possibility hung in the air like a question no one wanted to ask too loudly. Then they found another one, and another. 4 pulsing sources scattered across different parts of the sky, each with its own unique rhythm. That's when they knew this wasn't a message. This was a new type of astronomical object. Something no one had predicted, something that shouldn't exist according to the physics of the time. They called them pulsars, pulsating radio sources. And what Jocelyn Bell Burnell had discovered would reshape our understanding of stellar death gravity and the limits of matter itself. Scientists suggest that pulsars are neutron stars, the collapsed cores of massive stars that have exploded as supernovae. When a star much larger than our sun runs out of fuel, it can no longer support its own weight. The core collapses in on itself with such force that protons and electrons are crushed together, forming neutrons. What's left is an object roughly the size of a city containing more mass than the sun, spinning at unfathomable speeds. Imagine taking something heavier than the sun and compressing it until it's only about 12 miles across. A teaspoon of neutron star material would weigh about 1 billion tons on Earth. The gravity is so intense that if you stood on the surface, you'd be flattened to less than the width of an atom in a fraction of a second. Time itself would flow differently there, slower than anywhere else you could stand in the universe. But the truly remarkable thing about pulsars isn't just their density, it's their rotation. When a massive star collapses, it conserves angular momentum. Think of an ice skater pulling in their arms to spin faster. Now imagine that skater shrinking from the size of a solar system to the size of a small city. The resulting spin is almost incomprehensible. Some pulsars rotate hundreds of times per second. The fastest known pulsar, designated PSRJ 1748-2446 AD, spins 716 times every second. That's a city-sized object, heavier than the sun, rotating so fast that its surface is moving at roughly a quarter of the speed of light. Research shows that these spinning neutron stars have incredibly powerful magnetic fields, trillions of times stronger than anything we can create on Earth. As the pulsar rotates, these magnetic fields channel radiation out from the poles, creating beams of radio waves, X-rays, and gamma rays. If one of those beams happens to sweep across Earth as the pulsar rotates, we see a pulse. It's like a cosmic lighthouse rotating endlessly in the dark. The precision of pulsar timing is almost unsettling. Some pulsars are so regular that they rival atomic clocks in accuracy. Astronomers can predict when a pulse will arrive down to microseconds, sometimes nanoseconds, across years of observation. This isn't just impressive, it's useful. Scientists have proposed using pulsars as natural navigation beacons for spacecraft. If you're traveling through deep space and need to know your position, you can listen to several pulsars, compare the timing of their pulses, and triangulate your location with extraordinary precision. In fact, when NASA launched the Voyager spacecraft in 1977, they included a golden record with sounds and images from Earth. On the cover of that record is a diagram showing the position of our sun relative to 14 pulsars. The idea is that any civilization capable of finding and playing the record would also be able to identify those pulsars, use their known periods to calculate how much time has passed since the diagram was made, and pinpoint exactly when and where the Voyager was launched. It's a message written in the language of rotating neutron stars, a map made from cosmic lighthouses, and it will last for billions of years long after Earth itself might be unrecognizable. There's a common misconception about pulsars that's worth addressing. When people first learn about them, they sometimes imagine the star itself is pulsing, expanding, and contracting like a heartbeat. But that's not what's happening. The star isn't changing, it's spinning. The beams of radiation are constant, sweeping around like searchlights. We only see the pulse when the beam points at us. If you were observing from a different angle, you might see a different pulse rate or no pulses at all. The pulsar would still be there, still spinning, still beaming radiation into space. You'd just be standing in the wrong place to see it. This is important because it tells us something profound about observation and reality. The universe doesn't organize itself for our convenience. We see what we happen to be positioned to see. There could be thousands of pulsars whose beams never sweep across Earth, rotating forever in the dark undetected, simply because we're looking from the wrong angle. One of the most fascinating discoveries in pulsar research came in the 1980s, when astronomers found binary pulsar systems, where a pulsar orbits another star or another neutron star. These systems are extraordinary laboratories for testing Einstein's theory of general relativity. According to Einstein, massive objects moving through space should create ripples in space-time called gravitational waves. These waves carry energy away from the system, causing the orbits to slowly decay. In 1974, astronomers Russell Hulse and Joseph Taylor discovered a binary pulsar system designated PSRB, 1913 plus 16. By timing the pulses with extraordinary precision, they could track the orbit of the two neutron stars as they circled each other. And what they found was exactly what Einstein's equations predicted. The orbit was decaying at a rate that matched the expected energy loss from gravitational wave radiation. It was the first indirect evidence that gravitational waves exist. Hulse and Taylor won the Nobel Prize for the discovery. Decades later, in 2015, the LIGO experiment would detect gravitational waves directly for the first time, confirming what pulsar observations had already suggested. The universe is not a static stage. It's a dynamic fabric rippling with the motion of massive objects, and pulsars are precise enough to let us measure those ripples. Some pulsars are even stranger. Millisecond pulsars rotate so fast, they complete hundreds of revolutions per second. Scientists believe these are old neutron stars that have been spun up by accreting material from a companion star. As matter spirals onto the neutron star, it transfers angular momentum like water, hitting a water wheel, causing the pulsar to spin faster and faster until it reaches these extreme speeds. The fact that these objects can spin so quickly without flying apart tells us something fundamental about the nature of matter. The forces holding a neutron star together must be incredibly strong. We're talking about nuclear forces, the same interactions that hold atomic nuclei together, but operating on a cosmic scale. If a neutron star spun any faster, the centrifugal force at the equator would overcome gravity and the star would tear itself apart. The fastest pulsars are right at that edge, spinning as fast as physics allows. Here's a question to carry with you into sleep. What does it say about the universe that some of its most violent events, the explosive deaths of massive stars, create objects of such perfect regularity that chaos can give birth to precision? Pulsars are born in supernovae explosions, so powerful they outshine entire galaxies for weeks. The outer layers of the star are blasted into space at thousands of miles per second. The core collapses in milliseconds. Everything about the process is violent, chaotic, extreme. And yet, what emerges from that violence is an object that ticks like a metronome, steady and unchanging, for millions or even billions of years. It's as if the universe, having spent all its fury, settles into a kind of meditative rhythm. Spin and pulse, spin and pulse. A reminder that even in the wake of destruction, patterns emerge. Order arises. Time continues measured in the rotation of collapsed stars. The lesson of pulsars isn't about clocks or navigation or even physics. It's about resilience and transformation. These objects are remnants, the leftover cores of stars that no longer exist. Everything that made them stars, their light, their heat, their fusion reactions, is gone. What remains is dense dark and impossibly strange. But it's not dead. It's still doing something, still broadcasting, still marking time. In a way, pulsars are the universe's way of remembering. Each pulse is a heartbeat from a star that died long ago. Each rotation is a monument to something that once burned bright and then collapsed into something entirely new. They don't mourn what they were. They simply continue spinning in the dark, sending out their signals whether anyone is listening or not. Jocelyn Bell, Burnell, never won the Nobel Prize for discovering pulsars. The prize went to her supervisor and another senior scientist on the project. It was controversial then, and it remains controversial now. But Jocelyn herself has spoken about it with remarkable grace. She's said that the discovery was a team effort, that science is collaborative, that she's received many other honors, and that the work itself mattered more than the recognition. And the work has endured. Pulsars are now fundamental tools in astronomy. They help us test relativity, search for gravitational waves, measure cosmic distances, and understand the life cycles of stars. They're used to study the interstellar medium, detect planets around other stars, and even search for extremely low-frequency gravitational waves by timing arrays of pulsars across the sky. All because a young graduate student noticed a bit of scruff on a chart recorder and had the curiosity and patience to keep watching. As your thoughts drift towards sleep tonight, imagine those neutron stars out there spinning in the void. Imagine one rotating 700 times per second, a city-sized object moving so fast, its equator approaches the speed of light. Imagine the magnetic fields, the radiation beams, the perfect timing maintained across eons. And remember that the universe is full of these lighthouses scattered across the dark, each one marking time in its own unique rhythm. Each one a remnant of something that once lived and died and transformed into something stranger still. They're still spinning, still pulsing, still keeping perfect time in the endless night. Yet, for all their precision, pulsars and fast radio bursts share one thing in common. We understand them at least partly. We know what they are, even if we don't know every detail. But the Big Ear telescope, the same instrument that caught the wow signal, heard other things too. Dozens of them. Strong signals that arrived were recorded and then vanished into obscurity, overshadowed by that one famous red "Wow" scrawled in the margin. And some of those forgotten signals might be just as mysterious, just as important as the one that became legend. There's something haunting about fame, especially in science. One discovery becomes legendary, gets written into textbooks, discussed in documentaries, remembered by generations. And in its shadow, a dozen other mysteries fade into silence, recorded but never celebrated, documented but rarely examined. The WOW signal earned its place in history with a single red exclamation mark. But the Big Ear telescope heard other things too. Strange things. Signals that were logged, cataloged, and then quietly forgotten as funding dried up and attention moved elsewhere. Between 1973 and 1998, the Big Ear radio telescope in Ohio listened to the cosmos almost continuously. 25 years of patient observation, scanning the skies for anything unusual. The WOW signal arrived in 1977, but it wasn't alone. Buried in archives printed on long rolls of computer paper, now yellowing in storage, are dozens of other anomalous detections. Strong signals, brief appearances, patterns that don't quite fit the noise. Most researchers don't even know they exist. Because once you have one famous signal, one defining moment, everything else becomes a footnote. But those footnotes might be just as important as the headline. They might be pieces of a larger puzzle, clues to something we stopped looking for too soon. The Big Ear used a simple but elegant design. It was built in a natural depression, a rectangular reflector, about the size of 3 football fields pointing straight up at the zenith. As Earth rotated, different parts of the sky drifted through its field of view. Every 72 seconds, a new patch of space would come into focus, be observed, and then drift away, replaced by the next region. This design had advantages. It was cheap to build and operate, requiring no moving parts, no motors, no complex tracking systems. But it also had a significant limitation. Each patch of sky was only visible for 72 seconds. If something interesting appeared, there was no way to immediately swing the telescope back for a second look. You had to wait for Earth's rotation to bring that region around again, which could take days or even months, depending on the exact position. This is why the WOW signal was so frustrating. By the time Jerry Eman saw it on the printout, days had passed. The telescope had moved on. That specific patch of sky wouldn't return to the field of view for weeks. And when it did, there was nothing. Just silence. But here's what most people don't realize. The WOW signal wasn't the only strong, unexplained detection. It was just the one that someone happened to circle in red ink, the one that got attention, the one that sparked decades of speculation and research. The archives contain other signals, some almost as strong, some lasting longer, some repeating a few times before vanishing. Scientists suggest that many of these signals were likely interference glitches from satellites or ground-based transmitters bleeding into frequencies they shouldn't have been using. Research shows that radio telescopes, especially older ones, were vulnerable to all kinds of contamination. Aircraft radar systems, even microwave ovens could create signals that looked astronomical if you didn't know what to look for. But not all of them fit that explanation. Some appeared at frequencies that were heavily protected, where terrestrial interference should have been impossible. Some showed characteristics that don't match human technology. Some arrived from directions in the sky where there were no known sources, no satellites in orbit, no obvious explanation. Take, for example, a series of detections from early 1976, about a year before the WOW signal. The Big Ear recorded several strong bursts over the course of 3 weeks, all coming from roughly the same region of sky. Each burst lasted between 50 and 90 seconds, slightly longer than WOW. The frequency was similar within the protected hydrogen line. But because they didn't quite reach the intensity of the WOW signal, and because the pattern of their appearance was irregular, they were noted, filed, and largely ignored. What if those signals were related? What if they were attempts at communication messages that varied in length and strength, trying different approaches to get our attention? Or what if they were natural phenomena, some kind of sporadic cosmic event that we witnessed briefly and never investigated properly because we didn't have the resources or the motivation? We'll never know. The data exists preserved in archives, but the telescope is gone. Demolished in 1998, its reflective surface torn down to make room for expansion of a nearby golf course. The irony is almost painful. One of the most important instruments in the search for extraterrestrial intelligence, the telescope that detected the most famous potential alien signal in history, was destroyed to build recreational facilities. There's a pattern here worth noting. Throughout the history of astronomy, we've built instruments, made discoveries, and then abandoned the tools that brought us those insights, sometimes for good reasons, progress and newer technology, but often for mundane ones, funding cuts, changing priorities, lack of public interest. The Big Ear operated on a shoestring budget for most of its life. By the end, it was staffed primarily by volunteers, people who believed in the mission enough to donate their time. When the telescope was shut down, there was no comprehensive review of all the data it had gathered, no systematic analysis of every anomalous signal. The WOW signal was famous, so it got attention. Everything else was left in boxes, printouts, in storage data, on obsolete magnetic tapes that fewer and fewer people know how to read. This is one of the great tragedies of modern science. We generate data faster than we can analyze it. We make observations that might contain profound discoveries, but we lack the time, funding, or personnel to examine them properly. And then we move on, building new instruments, chasing new questions, leaving behind archives full of mysteries that no one has the resources to solve. Think about what might be hidden in those Big Ear archives. 25 years of observations, millions of data points, hundreds of anomalies flagged by the automated systems. Most of them probably nothing interference or calibration errors. But what if even 1% are genuine cosmic phenomena? That's still dozens of unexplained signals sitting in storage, waiting for someone to care enough to look. In the 1990s, a few researchers did try to conduct a more thorough review. They went through years of printouts looking for patterns, comparing signal strengths, trying to identify anything that resembled the WOW signal. They found several candidates, events that were strong, brief, and appeared at protected frequencies. But without the telescope to conduct follow-up observations, without funding for detailed analysis, the project stalled. One particularly intriguing case involved a signal detected in 1989, more than a decade after WOW. It came from a different part of the sky, but showed similar characteristics. Strong narrowband lasting about 60 seconds. The automated system flagged it. The observer on duty that night made a note. And then, like so many others, it faded into obscurity. What makes this especially frustrating is that by 1989, technology had advanced significantly. If researchers had known about this signal immediately, they could have contacted other observatories, coordinated follow-up observations, maybe caught it again. But the signal wasn't noticed until weeks later, when someone was reviewing old printouts. By then, the moment had passed. There's a lesson here about the nature of discovery. We like to think that important findings announce themselves, that the universe makes its mysteries obvious. But often the most significant observations are quiet, easily missed, buried in routine data. They require patience, attention, and the willingness to look at things that don't immediately seem important. Scientists believe that many astronomical phenomena are transient, appearing briefly and then vanishing perhaps forever. We live in an era of time-domain astronomy where telescopes are specifically designed to catch fleeting events. But before this modern approach, before automated alert systems and rapid response protocols, countless transient events probably occurred and went unnoticed. The Big Ear was ahead of its time, in some ways designed to catch brief, unexpected signals. But it was also limited by the technology and resources available. Printouts had to be reviewed by hand. Anomalies had to be noticed by tired observers working long shifts. Follow-up observations depended on weather telescope availability and funding that was never quite enough. Here's a question worth contemplating as you drift closer to sleep. How many other signals has humanity received and not recognized? How many times has the universe tried to tell us something, and we were too distracted to, underfunded, too focused on other things to listen properly? It's not just radio telescopes. Every instrument we point at the sky generates more data than we can fully process. Space telescopes like Hubble and Kepler have archives containing billions of images. Most of them have been analyzed by automated systems, but automated systems can only find what they're programmed to recognize. Unusual patterns, unexpected anomalies, things that don't fit our models might be sitting in those archives right now, waiting for a human eye to notice them. There's something deeply human about our tendency to focus on the famous, the celebrated, the one signal that got a name and a place in history. But the forgotten signals, the data points that never became stories, might be just as revealing. They might show us that anomalous cosmic signals aren't rare flukes, but part of a larger pattern we haven't recognized yet. Research in recent years has shown that the universe is far more dynamic and variable than we once thought. Fast radio bursts, which we discussed earlier, were unknown until 2007, but now we know they happen thousands of times a day. Gamma-ray bursts discovered in the 1960s, but not understood until the 1990s, are relatively common cosmic events. Gravitational waves detected for the first time in 2015 are now observed regularly. Each of these phenomena was once mysterious, unexplained, based on limited observations, and in each case it took years or decades of patient work to understand what was happening. The Big Ear's forgotten signals might be the same early detections of phenomena we haven't yet characterized, clues to cosmic events that are more common than we realize. Or they might be interference, glitches, errors. The mundane explanation is often the correct one. But we'll never know unless someone takes the time to look to analyze the data properly, to follow the threads that the original observers didn't have the resources to pursue. The demolition of the Big Ear in 1998 wasn't just the loss of an instrument. It was the closing of a chapter, the end of a particular way of doing astronomy. For 25 years, that telescope listened patiently, recording everything it heard, waiting for something extraordinary. And when extraordinary signals appeared, there was rarely enough support to investigate them fully. It's easy to blame budget cuts or administrative decisions, and those certainly played a role. But there's also a deeper issue about how science is funded and valued. Society tends to support projects that promise clear results, definite timelines, predictable outcomes. But listening for cosmic signals is inherently uncertain. You might listen for decades and hear nothing. Or you might hear something astonishing, but not be able to confirm it, leaving you with a mystery instead of an answer. The Big Ear gave us mysteries. The wow signal. The forgotten detections of 1976. The 1989 anomaly. Dozens of other brief, strong signals that appeared in the archives. These aren't failures, they're invitations. Questions the universe asked us, and we haven't finished answering. As you close your eyes tonight, think about those printouts in storage. Think about the signals that no one remembers the data, that no one analyzed the moments when the cosmos might have been trying to reach us, and we simply weren't ready to receive. And remember that sometimes the most important discoveries aren't the ones we celebrate, but the ones we overlook. The quiet signals waiting patiently in archives, hoping that someday someone will care enough to listen. But while some mysteries hide in forgotten data, waiting to be rediscovered, others are impossible to ignore, painted across the entire sky in a faint glow of microwave radiation. This signal doesn't come from a distant star or galaxy. It comes from everywhere at once, an echo of the universe's first light, carrying within it patterns that challenge everything we thought we understood about the cosmos itself. In 1964, two engineers at Bell Labs in New Jersey were trying to eliminate a persistent hiss from a sensitive radio antenna. Arno Penzias and Robert Wilson cleaned bird droppings from the dish, checked every connection, recalibrated the equipment, And still the noise remained. A faint uniform static coming from every direction in the sky, never changing, never fading. It was annoying, it was inexplicable, and it turned out to be the most important cosmological discovery of the 20th century. What they had found was the cosmic microwave background, the afterglow of the Big Bang itself. Light from when the universe was only 380,000 years old, stretched by cosmic expansion into microwave frequencies washing over Earth from all directions. It was proof that the universe had a beginning, that it was once unimaginably hot and dense, and that it had been cooling and expanding for nearly 14 billion years. Penzias and Wilson won the Nobel Prize. The cosmic microwave background became the foundation of modern cosmology, and for decades it seemed to confirm everything our theories predicted. A nearly perfect black-body spectrum, almost uniform temperature in every direction. The universe at its largest scales appeared smooth, symmetric, elegant. But when we looked closer, when we built more sensitive instruments and mapped the microwave sky with greater precision, we found something unsettling. The universe isn't quite as smooth as it should be. There are patterns in the cosmic microwave background that don't fit. Anomalies, cold spots, alignments that seem too precise to be random, and no one knows why. In 1992, NASA launched the Cosmic Background Explorer, known as COBE. Its mission was to measure the cosmic microwave background with unprecedented accuracy, looking for the tiny temperature fluctuations that seeded the formation of galaxies. And it found them, variations of only a few millionths of a degree scattered across the sky, like a map of the infant universe. These fluctuations were exactly what cosmologists expected, proof that the early cosmos wasn't perfectly smooth, that some regions were slightly denser than others, and that gravity could amplify those differences into the structures we see today. But COBE also found something unexpected. When scientists analyzed the data, they noticed that the largest fluctuations, the patterns spanning enormous angles across the sky, weren't randomly distributed. They seemed to align with each other in ways that shouldn't happen if the universe were truly isotropic, the same in all directions. Researchers called it the axis of evil, a somewhat tongue-in-cheek name for a genuinely disturbing finding. The quadrupole and octupole components of the cosmic microwave background, the largest scale patterns in the data, appeared to be aligned with the plane of the solar system and the ecliptic. It was as if the entire universe had some kind of preferred direction, or as if our local cosmic neighborhood had influenced the primordial radiation in ways that violated the cosmological principle. Scientists suggest this could be a statistical fluke, something that looks meaningful, but is actually just random chance. Research shows that when you analyze complex data with many parameters, you'll inevitably find some patterns that appear significant but aren't. The human brain is wired to see order in chaos faces and clouds, meaning incoincidence. Maybe the axis of evil is nothing more than pareidolia on a cosmic scale. But maybe it's not. Maybe it's telling us that the universe at its largest scales doesn't quite behave the way our simplest models predict. Maybe there's some kind of structure or influence that we haven't accounted for, something that breaks the perfect symmetry we assumed existed. In 2001, NASA launched a more sophisticated mission called the Wilkinson Microwave Anisotropy Probe, WMAP. It spent 9 years mapping the cosmic microwave background in even greater detail, confirming COBE's findings and adding new layers of precision. And the axis of evil remained. The alignment was still there, still unexplained, still troubling. Then, in 2013, the European Space Agency's Planck satellite began releasing its data, the most detailed map of the cosmic microwave background ever created. Scientists hoped it might resolve the anomaly, show that it was an artifact of previous instruments or a misinterpretation of the data. Instead, Planck confirmed it. The large-scale patterns in the cosmic microwave background really are aligned in ways that seem statistically unlikely. But Planck found something else too. a region of the sky about 15 degrees across where the cosmic microwave background is significantly colder than average. Not by much, only about 70 microkelvins, but enough to stand out against the surrounding temperature fluctuations. Researchers call it the cold spot, and it's one of the most perplexing features in all of cosmology. The cold spot sits in the southern celestial hemisphere, in the constellation Eridanus. It was first noticed in WMAP data, but dismissed as possible noise or a foreground contaminant. But when Planck confirmed its existence with independent measurements, astronomers had to take it seriously. This wasn't an error, it was a real feature of the universe. Scientists believe there are several possible explanations. One is that it's simply a statistical fluctuation, a region that happened by chance to be slightly emptier or slightly cooler when the universe was young. Unlikely but not impossible. The universe is vast and rare things do happen. Another possibility is more intriguing. Some researchers suggest the cold spot might be caused by a supervoid, an enormous region of space containing fewer galaxies than average. As light from the cosmic microwave background passes through this void, it loses energy through a process called the integrated Sachs-Wolf effect. The void expands as the light crosses it, and in an accelerating universe, this expansion causes a net cooling of the photons. Observations have found evidence for a large void in that direction, though it's not quite large enough or quite empty enough to fully explain the cold spot. So the mystery remains. Either the void is bigger than we think, or there's something else going on, some additional factor we haven't identified. A third possibility is more exotic. A small number of cosmologists have suggested that the cold spot could be evidence of a collision between our universe and another universe in the distant past. In some models of cosmic inflation, the process that drove the universe's rapid expansion in its first moments, multiple bubble universes can form. If two such bubbles collided before inflation ended, it might leave a signature in the cosmic microwave background, a circular region that looks different from the rest of the sky. This idea sounds like science fiction, and most cosmologists are deeply skeptical. There's no independent evidence for other universes, and invoking them to explain a single anomaly seems like a stretch. But the mathematics works the collision would produce a cold spot, roughly the size we observe, and it's at least theoretically testable. If we find other signatures of such a collision, patterns in the polarization of the microwave background, or specific types of temperature correlations, it would lend weight to the hypothesis. For now, the cold spot remains unexplained. A mystery written in the oldest light in the universe, a signal from when the cosmos was less than 400,000 years old. Still visible today, still defying our attempts at understanding. There's a common misconception about the cosmic microwave background that's worth addressing. Many people imagine it as a snapshot of the Big Bang itself, a picture of the moment of creation. But that's not quite right. The cosmic microwave background shows us the universe at a specific moment about 380,000 years after the Big Bang, when the cosmos had cooled enough for atoms to form and light to travel freely. Before that moment, the universe was a hot, dense plasma, where photons couldn't move more than a tiny distance without colliding with electrons. It was opaque, like trying to see through fog. But when the temperature dropped below about 3,000 degrees, Kelvin electrons combined with protons to form neutral hydrogen, and the fog cleared. Light that had been scattered endlessly suddenly had a clear path, and it's been traveling ever since, cooling as the universe expands, until now it reaches us as faint microwaves. So, the cosmic microwave background isn't the Big Bang, it's the echo of the moment when the universe became transparent. And that echo carries information encoded in tiny temperature differences about what the cosmos was like in its infancy. What makes the anomalies so troubling is that they suggest the universe might not have been as simple then as we thought. The standard model of cosmology, called lambda CDM, predicts that the early universe should have been almost perfectly homogeneous and isotropic. Small random fluctuations, yes, seeded by quantum effects during inflation. But no large-scale patterns, no preferred directions, no features that span billions of light years. The axis of evil and the cold spot challenge that assumption. They hint at something more complex, some structure or influence operating on scales larger than our theories comfortably allow. And the more precisely we measure the cosmic microwave background, the more these anomalies refuse to go away. Some scientists have proposed that the anomalies could be evidence of physics beyond the standard model. Perhaps inflation didn't happen exactly the way we think. Perhaps the universe has some kind of topology we haven't accounted for. Maybe it wraps around on itself in strange ways, creating patterns in the microwave background that look like alignments or voids. Others suggest the anomalies might be foreground effects, signals from our own galaxy or nearby structures that contaminate the data. The Planck team worked hard to remove these foregrounds, modeling the emission from dust synchrotron, radiation, and other local sources. But maybe there's something subtle they missed, some faint signal that mimics a cosmic anomaly. The truth is, we don't know. And that's both frustrating and exciting. Frustrating because we've spent billions of dollars building instruments to measure the cosmic microwave background with exquisite precision, and we still can't explain some of its most basic features. Exciting because unexplained observations are where breakthroughs happen. Every major advance in physics has started with data that didn't fit the prevailing theory. Here's a question to carry with you as you drift towards sleep. What if the anomalies in the cosmic microwave background are trying to tell us that the universe is fundamentally stranger than we've imagined? What if the simple, elegant models we've built are approximations that work well on small scales, but miss something essential about the cosmos as a whole? Think about how many times in the history of science we've assumed the universe was simpler than it actually is. We thought Earth was the center of everything. Then we thought the sun was. Then we thought our galaxy was the only galaxy. Each time observations forced us to expand our view, to accept that reality was bigger, more complex, more surprising than our theories allowed. The cosmic microwave background anomalies might be doing the same thing. They might be evidence that our current cosmological model, as successful as it's been, is still missing something. Not wrong exactly, but incomplete. A good approximation that works for most purposes but breaks down at the largest scales. Scientists are planning new missions to study the cosmic microwave background with even greater sensitivity. They want to measure its polarization, the direction in which the light waves oscillate, which carries additional information about the early universe. They want to look for signatures of gravitational waves from inflation ripples in space-time that should have left subtle imprints in the microwave sky, and they want to understand the anomalies, to determine once and for all whether they're real features of the cosmos or artifacts of observation, whether they're telling us something profound about the nature of the universe, or simply reminding us that even the best instruments and the most careful analysis can be fooled by random chance. The cosmic microwave background is the oldest thing we can see light that has been traveling toward us for nearly the entire history of the universe. It carries messages from a time when there were no stars, no galaxies, no planets, no life. Just energy and matter, cooling and expanding, beginning the slow process of assembling into the cosmos we inhabit today. And somehow, in that ancient light, there are patterns we can't explain, signals that challenge our understanding, whispers from the edge of space and time, asking questions we're only beginning to know how to hear. As you close your eyes tonight, imagine that light, those photons that have been traveling for billions of years, finally arriving at our telescopes, carrying their strange messages. Imagine the cold spot, a region of sky where the universe seems slightly emptier, slightly different. Imagine the axis of evil, those aligned patterns that shouldn't exist, that hint at symmetries we don't understand. And remember that the universe doesn't owe us simple answers. It doesn't organize itself according to our expectations. It simply is vast and ancient and strange, and every mystery we find is an invitation to look deeper, think harder, wonder more completely. The cosmic microwave background has given us some of our greatest confirmations of cosmological theory, but it's also given us some of our deepest mysteries, and perhaps that's exactly as it should be. Because science isn't about finding all the answers, it's about learning which questions to ask. Yet, while the cosmic microwave background speaks to us from the distant past, carrying messages from the infant universe, there are signals arriving from much closer from individual stars in our own cosmic neighborhood. And sometimes those signals are so bizarre, so resistant to natural explanation, that they force us to ask whether we might be seeing the work of intelligence technology operating on scales we can barely imagine. There's a particular kind of silence that settles over a room when someone presents data that shouldn't exist. When the numbers are right, the methodology is sound, but the implications are so strange that everyone stops talking and just stares at the screen. That's what happened in 2015, when astronomer Tabitha Boyajian stood before her colleagues and showed them what she'd found in data from NASA's Kepler Space Telescope. A star unremarkable in almost every way 1,400 light-years from Earth was doing something that no star should do. Its light was dimming, not a little, not gradually, but in massive irregular drops that reached as much as 22%. To understand why this is so bizarre, you need to know what astronomers expect when they watch a star. Most stars are steady, their brightness varying by tiny fractions of a percent, as they rotate or as star spots move across their surfaces. When a planet passes in front of a star, it blocks some of the light, creating a dip in brightness. But planets are small compared to stars. Even Jupiter, the largest planet in our solar system, would only block about 1% of the sun's light if it transited in front of it. An Earth-sized planet would block less than 1/100%. 22% is astronomical. Literally. To block that much light, you'd need something enormous, something far larger than any planet we know of. And whatever was blocking the star, designated KIC 8462852, later nicknamed Tabby's star, after its discoverer wasn't just big, it was irregular, asymmetric, appearing and disappearing in patterns that defied every model astronomers tried to fit to the data. The discovery came from citizen scientists, volunteers, who were reviewing Kepler data through a project called Planet Hunters. Kepler had been watching hundreds of thousands of stars, recording their brightness with exquisite precision, looking for the telltale dips that indicate planets. Most of the data analysis was automated, but human eyes are sometimes better at spotting unusual patterns, things that don't fit the template the software is looking for. And Tabby's star definitely didn't fit the template. Between 2009 and 2013, Kepler recorded multiple dimming events. In 2011, the star's brightness dropped by 15% over several days, then slowly returned to normal. In 2013, it dimmed by 22%, in an even stranger pattern, multiple dips happening in quick succession, like something enormous and irregular was passing in front of it. Scientists suggest several natural explanations. Perhaps it was a swarm of comets fragments from a shattered planet, or a disturbed comet cloud passing between us and the star. Research shows that comets can create irregular dimming patterns, especially if they're surrounded by clouds of dust and debris. If a family of comets happened to cross our line of sight at just the right time, it might explain what Kepler saw. But there are problems with the comet hypothesis. Comets typically orbit their stars in predictable paths, which means we should see repeated transits as they complete their orbits. Tabby's star showed no such regularity. The dimming events happened sporadically, with no obvious pattern to their timing or their depth. And to block 22% of the star's light, you'd need an absurdly large number of comets, more than seems plausible even in a recently disturbed system. Another possibility is that we are seeing the aftermath of a planetary collision, two large bodies smashing into each other and creating a massive debris cloud. Such events are thought to be relatively common in young stellar systems, as planets are still forming and orbits are still settling. But Tabby's star isn't young. It's a mature F-type star, somewhat larger and hotter than our Sun, but similar in age. Planetary collisions should be rare in such systems. Then there's the dust cloud hypothesis. Maybe the star is surrounded by an unusual concentration of interstellar dust, and we're seeing variations in that dust density as it moves through our line of sight. But observations of Tabby's star in infrared wavelengths where dust should glow brightly didn't show the excess emission you'd expect from large amounts of warm dust. The star looked normal in infrared, which doesn't match the dust cloud idea. Each natural explanation had flaws. Each left something unexplained. And that's when the more exotic hypotheses began to emerge. In September 2015, astronomer Jason Wright and his colleagues published a paper exploring what they carefully called more speculative scenarios. One of those scenarios was a Dyson swarm, a megastructure built by an advanced civilization to capture energy from their star. The concept comes from physicist Freeman Dyson, who proposed in 1960 that a sufficiently advanced civilization might eventually build structures around their star to harness its energy output. Not a solid shell which would be gravitationally unstable, but a swarm of satellite solar collectors, habitats, each one orbiting the star independently. From a distance, such a swarm might appear as irregular dimming, especially if the civilization was still in the process of building it, adding more structures over time. Wright was careful to emphasize that this was unlikely. The natural explanations, however incomplete, were still more probable than invoking alien engineering. But he also noted that it was worth considering, worth checking, because if there was even a small chance that we were seeing evidence of extraterrestrial technology, it would be the most important discovery in human history. The media predictably ran with the alien megastructure angle. Headlines proclaimed that scientists had found a Dyson sphere. Some articles suggested we were witnessing the construction of a galactic superstructure. The reality was more measured, more cautious, but the public imagination had been captured. Tabby's star became famous not for what we knew about it, but for what we couldn't rule out. Astronomers around the world began observing the star more carefully, using different telescopes, different wavelengths, trying to catch it in the act of dimming again. For years, nothing happened. The star remained steady, its brightness unchanging. Some researchers wondered if the original dimming events had been artifacts, errors in the Kepler data that looked like real signals but weren't. Then in May 2017, it happened again. Tabby's star began to dim, and this time, observers were ready. Telescopes across the globe swung toward it, capturing data in visible light, infrared, ultraviolet, building a comprehensive picture of what was happening. And what they found was both illuminating and puzzling. The dimming was wavelength dependent. Blue light was blocked more than red light, a signature consistent with small particles, dust grains, smaller than a micron scattering the starlight. This was important because it ruled out large, opaque objects. Planets' megastructures, anything solid, would block all wavelengths equally. The fact that blue light was preferentially scattered meant whatever was blocking the star was made of small particles consistent with dust. The alien megastructure hypothesis took a significant hit. Dust seemed more likely, but the mystery didn't disappear entirely. The wavelength dependence explained what was blocking the light, but it didn't explain where the dust came from, why it appeared so irregularly, or why the dimming events were so dramatic. Dust alone doesn't create 22% dips in brightness, unless there's an enormous amount of it, more than you'd expect from normal stellar processes. Scientists believe the most plausible explanation now involves some kind of disrupted planetary system. Perhaps a planet was torn apart by tidal forces, or perhaps a massive collision occurred, and we're seeing the long-term aftermath as the debris cloud slowly dissipates. The irregularity of the dimming could be explained by clumps of material in eccentric orbits passing in front of the star at unpredictable intervals. There's also evidence from historical records that adds another layer to the mystery. In 2016, researchers examined photographic plates from the Harvard College Observatory archives, images of the night sky taken over the past century. When they analyzed plates showing Tabby's star, they found something strange. Over the course of the 20th century, the star appeared to have dimmed by about 20%, a slow, gradual decline that wasn't matched by other nearby stars. This century-long dimming is hard to explain. Dust clouds don't last that long in close proximity to a star. They get blown away by stellar wind or fall into the star itself. Comets don't produce sustained dimming over decades. Planets definitely don't. Whatever is happening at Tabby's star, it's not a simple temporary phenomenon. It's something long-term, something ongoing, something we're only beginning to understand. Some researchers have questioned the century-long dimming, suggesting it might be an artifact of how the photographic plates were calibrated or processed. Different plates use different emulsions, different exposure times, different filters, and these variations can create false trends if you're not careful. But other nearby stars on the same plates don't show the same dimming, which argues that something real is happening at Tabby's star. Here's a question worth pondering as you drift closer to sleep. What does it say about us that our first instinct, when faced with something we can't explain, is to wonder if it might be artificial? Is it hope, loneliness? A deep desire to find evidence that we're not alone in the universe? The alien megastructure hypothesis was always a long shot, a possibility to consider, but not to embrace without extraordinary evidence. And as more data came in, as natural explanations improved, it became clear that we probably aren't looking at alien engineering. But the fact that we considered it seriously, that scientists published papers about it, and observatories devoted time to testing it, says something important about how we do science. We don't dismiss ideas just because they seem unlikely. We test them. We gather data. We let the universe show us what's real and what isn't. And if the data had pointed toward an artificial origin, if every natural explanation had failed, and the megastructure hypothesis was the only one that fit, we would have followed that evidence wherever it led. But the data didn't support it. The wavelength-dependent dimming, the infrared observations, the improved comet and dust models all point toward natural processes, however unusual or poorly understood. Tabby's star is strange, yes. It's doing things we don't fully grasp, but it's probably not a construction site for an alien civilization. That said, the star remains under observation. Astronomers continue to monitor it, waiting for the next dimming event, gathering more data, refining their models. Each new observation constrains the possibilities a little more, eliminating hypotheses that don't fit, strengthening those that do. It's slow work, patient work, the kind of careful science that doesn't make headlines but gradually builds understanding. There's a lesson here about the nature of discovery and the role of mystery in science. Tabby's star captured public imagination because it offered the possibility, however remote, of something extraordinary. An alien megastructure would be revolutionary proof that technological civilizations exist elsewhere, evidence that intelligence can reach scales we've only imagined. But the reality is almost certainly more mundane: a disrupted planetary system, an unusual dust cloud, natural processes we haven't fully characterized. And yet, the mundane explanation is still fascinating. Somewhere in space, 1,400 light-years away, a star is surrounded by something strange. Dust or debris or something we haven't quite identified, blocking huge amounts of light in irregular patterns, behaving in ways that challenge our models. It's a mystery. A smaller mystery than alien megastructures, perhaps, but a real one worth solving, worth the effort of observation and analysis. Scientists studying Tabby's star have learned to balance excitement with skepticism, to explore exotic possibilities while remaining grounded in what the data actually shows. It's a delicate balance, one that good science requires. You have to be open-minded enough to consider new ideas, but rigorous enough not to accept them without evidence. As you close your eyes tonight, Think about that distant star flickering strangely in the constellation Cygnus. Think about the citizen scientists who first noticed it, the astronomers who studied it, the telescopes that watched it dim and brighten in patterns no one predicted. Think about the hypotheses proposed and tested, the alien megastructures considered, and set aside the dust clouds and disrupted planets that remain as candidates. And remember that the universe is under no obligation to make sense to us immediately. Some mysteries take decades to solve, some take centuries, and some perhaps will remain mysterious for as long as we keep looking up, wondering, asking questions we're not yet ready to answer. Tabby's star taught us humility. It reminded us that the cosmos is still capable of surprising us, that even with our powerful telescopes and sophisticated theories, we can encounter phenomena that don't fit neatly into our understanding. And that's not a failure, that's an invitation. A reminder that there's still so much to learn, so much we haven't seen, so many signals waiting in the dark. The star still dims, the dust still blocks its light. The mystery continues quieter now than when it first captured headlines, but no less real, no less worthy of attention. And somewhere astronomers are still watching, still waiting for the next dimming event, still hoping that each new observation will bring them closer to understanding what's really happening in that distant stellar system. While Tabby's star challenged us with light that disappeared in irregular patterns, there's another kind of cosmic signal that arrives not as electromagnetic radiation at all, but as ripples in the fabric of space-time itself. These signals are so faint, so easily lost in noise, that we almost miss them entirely. And within the data we've gathered, there are hints of events so strange they force us to reconsider what we thought we knew about the universe's most extreme objects. On September 14th, 2015, at 09:50:45 UTC, both detectors of the Laser Interferometer Gravitational Wave Observatory registered something that shouldn't have been possible to detect. A ripple in space-time itself, a distortion so tiny that it changed the length of LIGO's 4-kilometer arms by less than 1,000th the diameter of a proton. The signal lasted only a fifth of a second, rising in frequency and amplitude like a chirp, then fading back into noise. And in that fraction of a second, everything changed, because for the first time in human history, we had heard the universe in a completely new way. Albert Einstein predicted gravitational waves in 1916, barely a year after he published his general theory of relativity. His equations showed that massive objects accelerating through space should create ripples in the fabric of space-time waves that propagate outward at the speed of light, stretching and squeezing everything they pass through. But Einstein himself doubted we'd ever detect them. The effect is so small, the distortion so infinitesimal, that building a detector sensitive enough seemed impossible. He was almost right. It took 100 years, billions of dollars, and technological innovations that didn't exist when Einstein made his prediction. But on that September morning, LIGO proved him wrong about our capabilities, even as it proved him right about the universe. The signal designated GW150914 came from two black holes, each about 30 times the mass of the Sun, spiraling into each other in the final moments before collision. They had been orbiting for millions or perhaps billions of years, gradually losing energy to gravitational wave radiation, moving closer and closer until their event horizons touched and they merged into a single larger black hole. In the final tenth of a second before merger, they were orbiting each other at nearly half the speed of light. The gravitational waves they produced carried away 3 solar masses worth of energy, converted directly from mass to radiation. According to Einstein's equation, energy equals mass times the speed of light squared. That's more energy than all the stars in the observable universe were producing at that moment, but released not as light, not as particles, but as ripples in the geometry of space and time itself. Scientists suggest that gravitational wave detectors like LIGO and Virgo have opened an entirely new window on the cosmos, Research shows that events we could never see with traditional telescopes, collisions of black holes that produce no light mergers of neutron stars and distant galaxies, perhaps even echoes from the Big Bang itself, can now be detected through the space-time ripples they create. It's like gaining a new sense, like suddenly being able to hear after a lifetime of silence. But within this flood of new data, there are anomalies. Signals that don't quite match our models, events that hint at physics we don't yet understand. The most intriguing of these is GW19052, one detected on May 21st, 2019. This wasn't just another black hole merger. This was something that, according to our best theories of stellar evolution, shouldn't exist at all. The signal showed two black holes colliding, but the masses were wrong. One was about 85 solar masses, the other about 66. When they merged, they created a black hole of about 142 solar masses. The remaining 9 solar masses were converted to gravitational wave energy. On the surface, this looks like every other black hole merger LIGO has detected. But there's a problem, a fundamental problem that shakes our understanding of how black holes form. According to stellar evolution and theory, when a very massive star exhausts its nuclear fuel and collapses, there's a range of masses where the core can't form a black hole directly. If the core is between about 65 and 130 solar masses, something called pair instability should occur. The star's core becomes so hot that photons start converting into electron-positron pairs, which reduces the radiation pressure holding the star up. The core collapses, triggering runaway nuclear fusion that completely destroys the star in a supernova so powerful it leaves nothing behind. No neutron star, no black hole, just expanding gas enriching the interstellar medium. This is called the pair instability mass gap. Stars in this range simply can't make black holes. And yet, here was a black hole of 85 solar masses sitting right in the middle of the gap where it shouldn't exist. How did it form? Where did it come from? One possibility is that it wasn't born from a star at all. It might be a second-generation black hole formed when two smaller black holes merged in a previous collision. If 240 solar mass black holes collided and merged, they could create an 85 solar mass black hole that bypasses the pair instability gap entirely. But this raises another question. Where did those original black holes come from? And how did they end up in a system where they could merge only for the resulting black hole to find another partner and merge again? Scientists believe this might happen in dense stellar environments like globular clusters or the centers of galaxies where black holes can sink toward the middle due to gravitational interactions, forming temporary pairs that eventually collide. Each merger creates a larger black hole that can participate in future mergers, building up mass over time. If this is correct, GW19052 might be evidence of hierarchical black hole growth, a process that could explain how supermassive black holes at the centers of galaxies reached millions or billions of solar masses. But there's another possibility more exotic and harder to test. Maybe some black holes don't form from stars at all. Maybe they are primordial, created in the extreme conditions of the early universe moments after the Big Bang. If density fluctuations in the infant cosmos were large enough, regions could have collapsed directly into black holes without ever forming stars. These primordial black holes could have any mass unrestricted by the limits of stellar evolution, and they might be lurking throughout the universe, occasionally colliding and producing gravitational waves. The challenge is distinguishing between these scenarios. Hierarchical mergers should produce black holes with spins that reflect their merger history. Primordial black holes might have different spin distributions or spatial clustering patterns. GW19052 alone doesn't give us enough information to decide. We need more detections, more statistics, more data to see which model fits better. What makes gravitational wave astronomy particularly challenging is the noise. LIGO is so sensitive that it can detect vibrations from ocean waves crashing on shores, thousands of miles away, seismic activity from earthquakes on the other side of the planet, even the occasional truck driving past the facility. Engineers have worked for decades to isolate the detectors from these disturbances, suspending the mirrors from elaborate vibration isolation systems, using active feedback to cancel out known sources of noise, employing algorithms to distinguish real gravitational waves from environmental glitches. But even with all these precautions, strange signals appear in the data. Brief bursts of noise that look almost like gravitational waves, but don't quite match the expected waveforms. Longer duration disturbances that drift through the detector's frequency range in ways that astrophysical sources shouldn't. Some of these are identified and removed, traced back to instrumental issues or environmental causes. Others remain mysterious, logged in databases, waiting for someone to understand what produced them. There's a particular type of anomaly called a glitch that has puzzled LIGO scientists since the beginning. These are brief transient disturbances in the detector output that come in characteristic shapes. Some look like sharp spikes, others like slow drifting waves. Some have been traced to scattered light bouncing around inside the instrument, others to subtle motion of the mirror coatings, and some have no known cause appearing randomly defying explanation. What makes glitches troubling is that they can mimic astrophysical signals. If a gravitational wave arrives at the same time as a glitch, it becomes incredibly difficult to extract the real signal from the noise. Sophisticated algorithms compare the data from LIGO's 2 detectors located in Louisiana and Washington state, looking for signals that appear in both simultaneously. True gravitational waves should arrive at both detectors with a time delay corresponding to the light travel time between them. Glitches are usually local to one detector, but sometimes glitches happen in both detectors at nearly the same time purely by chance, and those can be mistaken for weak astrophysical signals. Research shows that as LIGO becomes more sensitive, detecting fainter and more distant events, the problem of distinguishing real signals from noise becomes more acute. Every improvement in sensitivity brings more real gravitational waves into the detectable range, but it also makes the detector more vulnerable to subtle environmental effects. It's a constant battle fought with better isolation systems, more sophisticated data analysis, and careful validation of every detection. One of the strangest aspects of gravitational wave observations is something called the stochastic background. This is a faint, persistent hum of gravitational waves coming from all directions, produced by countless unresolved sources throughout the universe. Imagine standing in a crowded room where everyone is whispering. You can't make out individual conversations, but you can hear the overall murmur. The stochastic background is like that. A sea of gravitational waves from mergers too distant or too weak to detect individually, all blending together into a background noise. Scientists suggest this background might contain information about the early universe. Gravitational waves produced during cosmic inflation or phase transitions in the first moments after the Big Bang. If we could measure it precisely enough, we might learn about conditions when the universe was less than a second old, long before any light could escape the hot, dense plasma that filled space. But detecting the stochastic background requires extraordinary sensitivity and long observation times, carefully correlating data from multiple detectors to pick out the faint signal from instrumental noise. As of now, we haven't definitively detected the stochastic background. We've placed upper limits on how strong it can be, ruling out some theoretical models, but the signal itself remains just below our current sensitivity threshold. Their scientists are confident of that, but it's too faint to see clearly. Future detectors, more sensitive than LIGO, might finally bring it into view. Here's a question to carry with you as sleep draws nearer. What does it mean that we can now feel the universe breathing, detect the tremors when massive objects collide billions of light years away, sense ripples in the very fabric of reality? What does it change about our place in the cosmos when when we can listen to space-time itself. There's something profoundly humbling about gravitational wave astronomy. We're not just looking at the universe anymore, we're feeling it. Every detected merger is a physical sensation, a tiny squeeze and stretch of the Earth itself, of our bodies, of the atoms we're made from. When those black holes collided 7 billion light years away, releasing more energy in a fraction of a second than all the stars in the visible universe combined, the ripples they created eventually reached us. And for a fifth of a second, we trembled in response. The common misconception about gravitational waves is that there's something happening out there in space separate from us. But that's not right. When a gravitational wave passes through Earth, it passes through everything. Through the ground, through buildings, through our bodies. The distances between atoms change ever so slightly. The length of your arm increases and decreases by an amount far too small to feel but real nonetheless. We're not observers standing outside the phenomenon. We're part of it, participants in these cosmic events connected by geometry to everything that moves and breathes and collides in the universe. Scientists are planning next-generation detectors that will be even more sensitive than LIGO. The Einstein Telescope in Europe, Cosmic Explorer in the United States, projects that will increase our detection range by 10 times or more, allowing us to observe black hole mergers from the edge of the observable universe from when the cosmos was only a few 100 million years old. And they're planning space-based detectors like LISA, the Laser Interferometer Space Antenna, which will have arms millions of kilometers long and be sensitive to lower frequency gravitational waves that Earth-based detectors can't see. With these new instruments, the anomalies we're seeing now, the mysterious mergers in the mass gap, the unexplained glitches, the hints of a stochastic background, will either resolve into understood phenomena or deepen into more profound mysteries. We'll detect thousands of mergers per year instead of dozens. We'll see neutron stars colliding in real time, watch black holes form, perhaps even catch gravitational waves from supernovae or from exotic objects we haven't imagined yet. But we'll also face new challenges. More detections mean more data, more complexity, more opportunities for subtle errors to creep into our analysis. The universe doesn't care about our ability to understand it. It will show us what it shows us, and we'll have to work to make sense of it. Building better models, testing new theories, confronting our assumptions when the data doesn't fit. As your thoughts drift toward rest, imagine those ripples flowing through you right now. Gravitational waves from mergers happening across the universe, too faint for our current detectors, but real nonetheless. Stretching and squeezing the space between your atoms, connecting you physically to events unfolding billions of light years away. You are not separate from the cosmos. You're woven into it, part of the same fabric that black holes distort and gravitational waves ripple through. And remember that we almost missed this entirely. For 100 years after Einstein's prediction, gravitational waves remained theoretical, undetected, a beautiful consequence of the equations that no one was sure would ever be observed. The technology didn't exist. The funding wasn't available. Many physicists thought it was a waste of time to even try, but a few people persisted, building prototypes, improving designs, convincing skeptics to support the project. And on September 14, 2015, all that patience paid off. The universe reached out and touched us, sent us a message written in the language of curved space-time, and we were finally ready to receive it. The signals keep coming. The detectors keep listening. And within the data hidden among confirmed detections and understood noise, there might be other mysteries waiting, other anomalies that will one day force us to expand our theories, question our assumptions, and recognize once again that the universe is stranger and more wonderful than we dared to imagine. These ripples in space-time have taught us to listen in ways we never could before, to feel the universe's most violent moments as they echo across billions of years. But as we gather more observations, compile more data, and build better instruments, We're discovering that the cosmos might be sending us not just individual signals, but a constant underlying murmur we've only just begun to detect. In June 2023, multiple teams of astronomers made simultaneous announcements that sent quiet ripples through the scientific community. After 15 years of patient observation, analyzing the precise timing of dozens of pulsars scattered across our galaxy, they had detected something extraordinary. Not individual gravitational wave events like LIGO observes not the sharp chirps of colliding black holes, but something deeper, more persistent. A low-frequency hum pervading the entire universe, a background chorus of gravitational waves so faint and so pervasive that it took decades of data to even glimpse it. This wasn't a signal from one source. It was a symphony from everywhere, the combined gravitational radiation from thousands, perhaps millions of events throughout cosmic history, all blending together into a continuous drone that vibrates through space-time itself. And what makes it mysterious isn't just that it exists, but that some aspects of what we're detecting don't quite match what we expected to find. The technique used to discover this background is elegant in its simplicity. Pulsars, as we discussed earlier, are nature's most precise clocks. They spin with incredible regularity, sending out pulses of radio waves that arrive at Earth with timing that can be predicted down to nanoseconds. But if a gravitational wave passes between us and a pulsar, it stretches and compresses the space the radio waves travel through, causing the pulses to arrive slightly early or slightly late. By monitoring dozens of pulsars simultaneously and looking for correlated timing, variations astronomers can detect gravitational waves with wavelengths measured in light years far too long for instruments like LIGO to sense. This approach is called pulsar timing arrays, and it requires extraordinary patience. You can't just watch pulsars for a few months and expect to see anything. The gravitational waves being searched for have periods of years or decades. To detect them, you need to time pulsars consistently for at least a decade, preferably longer, building up enough data to distinguish the subtle correlations caused by gravitational waves from random noise and other timing variations. The North American Nanohertz Observatory for Gravitational Waves, known as NanoGrav, began operations in 2007. Similar projects started in Europe, India, and Australia. For years, they published upper limits measurements showing that if a gravitational wave background existed, it had to be below a certain strength. But they kept observing, kept timing, their pulsars kept accumulating data, and in 2020, they began to see hints. Correlations in the timing residuals that matched the expected signature of gravitational waves. The signal was weak, barely above the noise, but it was there. By 2023, with 15 years of data from multiple independent pulsar timing arrays, the evidence had become compelling. The gravitational wave background is real. It exists, and it's stronger than some theoretical predictions suggested it should be. Scientists suggest the most likely source of this background is supermassive black hole binaries, pairs of black holes millions or billions of times more massive than the Sun, orbiting each other at the centers of merging galaxies. Research shows that when two galaxies collide, their central black holes eventually sink toward the center of the merged galaxy and form a binary system. These binaries take millions of years to spiral together, and during that time, they emit powerful gravitational waves at frequencies that pulsar timing arrays can detect. Throughout the observable universe, galaxy mergers are common. At any given moment, thousands of supermassive black hole binaries are orbiting, radiating gravitational waves. And all of those signals from near and far from different stages of their orbital evolution combine into a stochastic background, a sea of overlapping waves that creates the hum we're now detecting. But here's where it gets interesting. The strength of the signal we're seeing is slightly higher than the simplest models predict. Not drastically higher, not so much that it breaks our theories, but enough to make astronomers wonder if something else might be contributing. Maybe supermassive black holes are more common than we thought. Maybe they merge faster than our models suggest. Or maybe there's another source of low-frequency gravitational waves we haven't accounted for. One possibility is cosmic strings, hypothetical one-dimensional defects in space-time that might have formed in the early universe during phase transitions. Think of them as cracks in the fabric of space, infinitesimally thin, but stretching across cosmic distances, containing enormous amounts of energy. If cosmic strings exist, and if they occasionally form loops that oscillate and decay, they would produce gravitational waves spanning a wide range of frequencies, including the nanohertz band that pulsar timing arrays observe. Cosmic strings are entirely theoretical. We've never seen direct evidence for them. They emerge from certain models of particle physics and cosmology, but whether they actually exist in our universe is an open question. If the excess signal in the pulsar timing data turns out to be real and can't be explained by supermassive black hole binaries alone, cosmic strings become a more intriguing possibility, but it's too early to make that claim. The data is still noisy, the uncertainties are large, and more observation time is needed to be certain. Another exotic possibility involves the early universe itself. During the first fractions of a second after the Big Bang, the cosmos underwent rapid expansion called inflation. Some models of inflation predict that quantum fluctuations during this period could have generated gravitational waves that persist to the present day, redshifted by cosmic expansion into the low-frequency range that pulsar timing arrays detect. If we're seeing evidence of primordial gravitational waves, it would be an unprecedented window into physics at energy scales we can never hope to reproduce in particle accelerators. But again, this is speculative. The most straightforward explanation remains supermassive black hole binaries, and most astronomers believe that's what we're detecting. The challenge now is to move from detection of the background as a whole to resolving individual sources. With more data and better analysis techniques, it might eventually be possible to pick out the loudest supermassive black hole binaries from the background to identify specific systems and watch them evolve over time. There's something deeply moving about the idea that we're swimming in gravitational waves. Every moment of everyday space-time around us is rippling with the echoes of cosmic events both recent and ancient. Black holes colliding billions of light years away, supermassive binaries orbiting in distant galaxy clusters, perhaps even remnants of phase transitions from the universe's first moments. All of it washing over us, imperceptible to our senses, but real, measurable, a constant reminder that the cosmos is dynamic, active, never truly still. Think about what it means to detect something this subtle. The timing variations caused by the gravitational wave background amount to delays or advances of only a few hundred nanoseconds over years of observation. That's the equivalent of detecting a change in the distance to a pulsar of about 100 meters, when the pulsars themselves are hundreds or thousands of light years away. It's like measuring the width of a human hair from across the continent. And yet, with careful observation, sophisticated statistics, and years of patient data collection, we can do it. There's a common misconception about the gravitational wave background that's worth addressing. Some people imagine it as a kind of cosmic noise that interferes with detecting individual gravitational wave events. But it's not noise in that sense. It's signal. It's information. Just like the cosmic microwave background tells us about the universe when it was 380,000 years old, the gravitational wave background tells us about massive objects and cosmic structures throughout the history of the universe. It's another layer of reality, another way the cosmos communicates its story. Scientists believe that as pulsar timing arrays continue to gather data, the characterization of the gravitational wave background will improve dramatically. Already with 15 years of data, the detection is solid. With 20 or 30 years, we'll be able to measure its spectrum, precisely determine whether it's purely from supermassive black hole binaries, or if there are contributions from other sources, and possibly even resolve the strongest individual binaries. But there are challenges. Pulsars aren't perfect clocks. They have their own timing noise, subtle irregularities in their rotation that can mimic gravitational wave signals. Distinguishing between intrinsic pulsar noise and gravitational wave-induced timing, variations requires careful modeling and cross-correlation between many pulsars. The more pulsars you monitor, the better you can separate the signals. Currently, the major pulsar timing arrays monitor between 40 and 70 pulsars each. Future efforts might expand this to hundreds, creating a galaxy-wide network of natural gravitational wave detectors. Each new pulsar added to the array improves sensitivity and helps confirm or rule out correlations. It's slow work adding one pulsar at a time, timing them month after month, year after year. But it's the only way to probe this frequency range of gravitational waves. There's also the question of what happens when pulsar timing arrays and space-based detectors like LISA come online. LISA, planned for launch in the 2030s, will be sensitive to gravitational waves at frequencies between pulsar timing arrays and ground-based detectors like LIGO. It will see individual supermassive black hole binaries as they spiral toward merger, tracking their evolution in real time. By combining observations from pulsar timing arrays, which detect the early stages of these mergers, and LISA, which sees the final coalescence, we'll be able to follow supermassive black hole binaries through their entire life cycle. Here's a question to ponder as your mind drifts toward rest. What does it feel like to live in a universe where space-time itself is never still, where the geometry of reality is constantly shifting in response to distant events, where even in the apparent silence of empty space, there's a persistent hum of gravitational radiation from uncounted sources? The detection of the gravitational wave background marks a transition in astronomy. We've moved from detecting individual rare events to perceiving the collective behavior of cosmic populations. It's like the difference between seeing individual raindrops and feeling the rain itself. Both are important. Both tell us something about the weather, but they're different kinds of knowledge, different perspectives on the same underlying reality. As more data comes in, as the signal becomes clearer and the uncertainties shrink, we'll learn more about the population of supermassive black holes in the universe. How common are they? How massive do they grow? How often do they merge? Do their properties change with cosmic epoch, with the age of the universe? The gravitational wave background holds answers to all these questions, encoded in its spectrum, its strength, its statistical properties. And if there are surprises, if the background turns out to be stronger than expected or shows features we didn't predict, that will be even more interesting. Because surprises are where we learn. They're the universe's way of telling us that our models are incomplete, that there's something we've missed, some piece of the puzzle we haven't yet found. Scientists studying the gravitational wave background are in a unique position. They're listening to a signal that's been present for billions of years, that existed long before humans evolved, before Earth formed, before our solar system condensed from a cloud of interstellar gas. And now, finally, we have the technology and the patience to hear it, to recognize the hum that's always been there, the cosmic vibration we were deaf to until just recently. As you close your eyes tonight, imagine that hum surrounding you. Not as sound, but as gentle waves in space-time, stretching and compressing the distances between atoms, flexing the fabric of the universe itself. Imagine supermassive black holes orbiting in distant galaxies, their motion sending ripples outward at the speed of light. Ripples that travel for billions of years before reaching Earth, before passing through your body, before continuing on into the cosmic dark beyond. And remember that we're not separate from these phenomena. We're part of the same universe that produces them. The atoms in your body were forged in stars that eventually died, some as supernovae, some as neutron stars, some as black holes. The calcium in your bones, the iron in your blood, the oxygen you breathe, All of it came from stellar processes, from fusion and collapse, and the recycling of matter through generations of stars. You are made of stardust. And now, with gravitational wave astronomy, we're learning to feel the universe's heartbeat, to sense the rhythm of cosmic events that shape the matter we're made from. The gravitational wave background will continue to reveal its secrets slowly, patiently, as we gather more years of pulsar timing data. And within that growing data set, there might be other mysteries waiting. Unexpected features in the spectrum, hints of sources we haven't imagined, anomalies that will send us back to our theories, our models, our assumptions about how the universe works. Science isn't about having all the answers. It's about asking better questions, building better instruments, listening more carefully to what the universe is trying to tell us. And sometimes, if we're patient enough, persistent enough, we discover that the cosmos has been speaking to us all along. We just needed to learn the language. We've drifted through signals from across the universe, from the brief whisper of the wall to the persistent hum of gravitational waves. We've encountered mysteries that span seconds, and mysteries that span billions of years. And through all of it, one truth has emerged again and again. The universe is not silent. It speaks in radio waves, enlightened gravitational ripples, and microwave echoes. But perhaps the deepest lesson these cosmic signals teach us isn't about what we found. It's about what we haven't. About the beauty that lives in questions without answers, in the space between knowing and wondering. We've traveled far tonight. From a 72-second signal in Ohio that made a man write, "Wow" in red ink, to millisecond bursts arriving from billions of light years away. From neutron stars spinning hundreds of times per second, with the precision of atomic clocks, to forgotten signals buried in archives that no one remembers to examine. We've explored cold spots in the cosmic microwave background that might be windows into other universes, stars that dim in ways no planet can explain, and ripples in space-time itself, carrying messages from the most violent events the cosmos can produce. And through all of it, one pattern has emerged. The universe is not silent. It's speaking constantly in languages we're only beginning to understand, through channels we've only recently learned to monitor. Every telescope we build, every detector we activate, every archive we examine reveals new mysteries, new questions, new invitations to look deeper and wonder more carefully. But here's what's remarkable. These mysteries don't diminish us. They don't make us smaller or less significant. They do exactly the opposite. Every unexplained signal, every anomaly that defies our models, every pattern that shouldn't exist according to our theories, is evidence that the universe is more interesting than we thought, more complex, more worthy of our attention and our awe. Think about what we've accomplished in just over a century. In 1900, we didn't know that galaxies existed beyond our own. We thought the Milky Way was the entire universe. We had no concept of black holes, no understanding of neutron stars, no knowledge of cosmic expansion or the Big Bang. We couldn't detect radio waves from space. We'd never seen a gravitational wave. The idea of timing pulsars to detect space-time ripples would have seemed like fantasy. And now, barely 4 generations later, we're listening to the universe in ways our ancestors couldn't have imagined. We're detecting signals from when the cosmos was less than a second old. We're watching black holes collide in real time. We're mapping the distribution of matter across billions of light years. We're searching for evidence of other civilizations, other intelligences, other voices in the cosmic conversation. Scientists suggest that we're living through a golden age of astronomy, a period when new discoveries are happening faster than we can fully digest them. Research shows that the number of known exoplanets, detected gravitational wave events, and mapped galaxies is increasing exponentially. Every year brings instruments with greater sensitivity, algorithms with better pattern recognition, collaborations that span continents and combine data in ways that wouldn't have been possible even a decade ago. But with all this progress, with all these discoveries, the fundamental mysteries remain. We still don't know what sent the wow signal. We still can't fully explain fast radio bursts or predict when they'll occur. We don't understand the cold spot in the cosmic microwave background or the axis of evil that seems to align cosmic structures in impossible ways. We can't say with certainty what dimmed Tabby's star or whether there are artificial structures anywhere in the universe. And the gravitational wave background we've detected raises as many questions as it answers. This is not a failure. This is exactly how science should work. We don't seek neat final answers that close off inquiry. We seek better questions, more precise measurements, deeper understanding that inevitably reveals new layers of complexity we didn't know existed. Every mystery solved opens up new territories of ignorance, new frontiers to explore. There's a kind of humility required to do this work. You have to be willing to say, I don't know. You have to be comfortable with uncertainty, with the possibility that your favorite theory might be wrong, that the universe might not operate the way you hoped or expected. You have to accept that some questions might not be answerable in your lifetime, that you might spend decades studying something without ever reaching a definitive conclusion. And yet, scientists keep working, keep building telescopes, keep analyzing data, keep proposing hypotheses and testing them against observation. Not because they're certain they'll find answers, but because the search itself is meaningful. Because every measurement, every observation, every carefully gathered data point brings us incrementally closer to understanding, even if complete understanding remains forever out of reach. Here's something worth considering as you prepare for sleep. What if the mystery is the point? What if the universe isn't designed to be fully knowable, at least not by minds like ours and time frames we can comprehend? What if the endless layers of complexity, the signals we can't explain, the patterns that almost make sense but not quite, are invitations to keep looking, keep wondering, keep pushing the boundaries of what we can observe and measure? The wow signal taught us that the cosmos can surprise us, that a single event lasting barely more than a minute can capture human imagination for decades. Fast radio bursts showed us that the universe is far more dynamic and violent than we realized, that powerful events we never predicted are happening constantly everywhere. Pulsars demonstrated that even in death, stars can create beauty, can keep time with a precision that rivals our best technology, can serve as natural laboratories for testing the fundamental laws of physics. The forgotten signals in the Big Ear archives remind us that history is full of overlooked data, that sometimes the most important discoveries are the ones we almost made the observations we recorded, but didn't recognize as significant until it was too late to follow up. The cosmic microwave background anomalies challenge our assumption that the universe should be simple and symmetric, that the largest scales should be the easiest to understand. Tabby's star showed us that even in an age of advanced astronomy, we can still find individual objects that behave in ways we can't explain. That the alien megastructure hypothesis, however unlikely, deserves serious consideration when we encounter the truly anomalous. And gravitational waves, both the individual events and the persistent background, opened an entirely new way of experiencing the universe, allowing us to feel cosmic events rather than just see them. Each of these mysteries has something to teach us beyond the specific scientific questions they raise. They teach patience, they teach rigor, they teach us to hold our conclusions lightly, to remain open to new evidence, to distinguish between what we know, what we think we know, and what we're just guessing at. They teach us that the universe doesn't owe us explanations, that nature operates according to its own rules, not according to our convenience or our theories. And they teach us something about being human, about our place in a cosmos so vast that light from distant galaxies takes billions of years to reach us, about our capacity for curiosity, for wonder, for persistent investigation in the face of overwhelming complexity, about our ability to build instruments sensitive enough to detect changes smaller than an atomic nucleus, to coordinate observations across the globe, to collaborate across borders and generations in pursuit of understanding. The signals we've discussed tonight are just a tiny sample of cosmic mysteries currently puzzling astronomers. There are gamma-ray bursts we can't explain, strange orbits in the outer solar system that hint at undiscovered planets, fast-moving stars ejected from the galactic center at speeds that shouldn't be possible, galaxies that seem to rotate too quickly given their visible mass, leading to theories of dark matter we still haven't directly detected, cosmic voids where almost no galaxies exist, empty regions hundreds of millions of light-years across. Every branch of astronomy has its anomalies, its unexplained observations, its signals that don't quite fit. And that's wonderful. That's how it should be. Because if we ever reached a point where everything made sense, where every observation fit our models perfectly, where there were no more mysteries to investigate, science would stop. Not because we'd learned everything, but because we'd stopped being curious enough to notice what doesn't fit. The truth is, we'll probably never know what caused the WOW signal. Jerry Ehman passed away in 2022, never having seen his discovery explained. The Big Ear telescope was demolished decades ago. The technology to conduct proper follow-up observations didn't exist when the signal was detected, and by the time it did, whatever produced the signal was long gone or had stopped transmitting. It's frustrating, it's unsatisfying, and it's also perfectly appropriate because the universe is under no obligation to repeat itself for our benefit. But that doesn't make the WOW signal any less important. It happened. It was recorded. It reminded us that we don't know everything about what's out there, that unexpected things can occur, that the search for cosmic signals is worth continuing even if most of the time we hear nothing but static. One signal in 45 years of observation might seem like a poor return on investment, but it only takes one genuine detection, one confirmed message from beyond Earth to change everything. As for the other mysteries we've explored, some will likely be solved. Fast radio bursts are already becoming better understood as we detect more of them and develop more sophisticated models. The gravitational wave background will be characterized more precisely as pulsar timing arrays accumulate more years of data. Tabby's star might finally reveal its secrets when next-generation telescopes can study it in wavelengths and at resolutions currently impossible. But other mysteries might persist for decades or even centuries. The cosmic microwave background anomalies might require observations we can't make from within our local cosmic neighborhood. The forgotten Big Ear signals might remain forever unconfirmed, their data preserved, but their causes unknowable. And there will be new mystery signals we haven't detected yet. Phenomena we haven't imagined, questions we don't yet know how to ask. That's the nature of this work. That's the beauty of it. Science isn't about reaching a destination. It's about the journey, the process of looking and measuring and wondering. It's about being humble enough to admit ignorance while being bold enough to keep searching anyway. It's about building better tools, asking better questions, and accepting that every answer leads to more questions, deeper layers, further mysteries. So, what should we take from all of this? What's the lesson of these mysterious cosmic signals? Perhaps it's simply this. The universe is vast and strange and full of things we don't understand. But we can listen. We can watch. We can build instruments that extend our senses into realms our biology never prepared us for. We can detect the invisible, measure the unmeasurable, and occasionally catch glimpses of something so strange, so unexpected, that it forces us to reconsider everything we thought we knew. And that's enough. That's more than enough. Because in a cosmos that could have been silent, simple, and boring, we find ourselves in one that speaks constantly in 1,000 different voices, that reveals new complexity at every scale we examine, that rewards our curiosity with mysteries worth spending lifetimes trying to solve. The signals are out there, right now. Fast radio bursts are flashing across the universe, their light just beginning. Journeys that will take billions of years to complete. Pulsars are spinning, keeping perfect time in the darkness. Gravitational waves are rippling through space-time, carrying news of collisions and mergers from the distant past. And somewhere, maybe another signal like WOW is arriving, washing over Earth, waiting for someone to notice it, to circle it on a printout, to spend decades wondering what it might mean. We are the ones who listen, the species that points instruments at the sky and asks questions, the conscious matter that looks back at the universe that made it and tries to understand. We're made of atoms forged in stellar cores, organized by evolution into patterns complex enough to wonder about our origins. We're the universe examining itself, asking questions about its own nature, its own history, its own vast and intricate structure. And every signal we detect, every mystery we encounter, every anomaly we can't quite explain is a gift. Evidence that there's more to learn, more to discover, more reasons to keep looking up, keep listening, keep wondering what else might be out there in the cosmic dark waiting to be found. As you drift off to sleep tonight, let these thoughts settle gently. Let the mysteries rest beside you, like old friends. You don't need to solve them. You don't need to understand everything. You just need to know that they're there, that the universe is bigger and stranger and more wonderful than we can fully grasp. And that's exactly as it should be. Sleep well knowing that somewhere in the night sky, signals are traveling, pulsars are ticking, black holes are colliding, fast radio bursts are flashing, and the cosmic microwave background is glowing softly with the light of creation, carrying patterns we're still learning to read. Thank you for joining me on this quiet journey through the mysteries of cosmic signals. Thank you for your curiosity, your patience, your willingness to sit with questions that have no easy answers. Thank you for being the kind of person who finds beauty in mysteries, who can appreciate the unknown without needing to immediately explain it away. If this journey resonated with you, if these mysteries sparked something in your mind, there will be more stories waiting. More quiet explorations of the cosmos, more gentle investigations into the nature of reality. More chances to drift through the universe's greatest puzzles with a voice that speaks softly and a wonder that never fades. For now, rest. Dream gently. And remember that the universe is still whispering, still sending its signals across the void, still waiting for us to listen. Good night,